Ever wondered how AI can decode the brain's hidden messages, or why some brain scans look different from person to person? Let's dive into three groundbreaking studies, reshaping neuroscience and machine learning. First, a 2017 paper by Ball used convolutional neural networks, or CNNs, to decode EEG data. You know EEG from those headsets that track brainwaves. Ball's team trained AI to spot patterns in that electrical chatter, like figuring out what someone's thinking just by their brain's buzz. But here's the cool part. They didn't just decode the data, they visualized it, turning abstract signals into maps of brain activity. Think of it like giving the brain a voice, helping us understand how thoughts emerge from electrical noise. Now let's shift focus to functional near-infrared spectroscopy, fNIRS, a non-invasive brain imaging technique that measures blood flow using light. It's like a brain scanner that tracks oxygen levels in real time, but the signals it captures are messy, noisy, variable, and full of interference. This is where deep learning steps in, using neural networks to untangle the chaos. But here's the key. The activation functions in these networks, those mathematical rules that determine how neurons fire, are critical. They're the traffic controllers of the network, shaping how information flows. Most researchers default to ReLU, rectified linear unit, a simple, fast function that ignores negative values. But a recent study asked, what if other activation functions could do better for fNIRS data? The team tested 7 functions, ReLU, ELU, swish, sigmoid, Tanh, square, and absolute, across 4 neural network architectures, including a specialized design called fNIRS net. All models were trained on the same dataset, brain activity from participants listening to sounds, with trials labeled as deviant or standard tones. Here's where it gets technical. fNIRS signals have bidirectional variations. They rise and fall like a heartbeat. Symmetrical functions like Tanh and absolute, which mirrors negative values, were tested against ReLU's asymmetry. The results? Symmetry mattered. Tanh achieved 83.66% accuracy in one network, while the absolute function outperformed others in deeper architectures. Why? Because fNIRS data often centers around 0, and symmetry helps models detect subtle polarity shifts, like tracking whether a signal is increasing or decreasing. But the twist? A modified absolute function with an alpha parameter of -1, which scales negative values, beat others in tests. This tweak preserved the polarity of signals, a critical feature for fNIRS. Meanwhile, square and ELU lagged, with ReLU underperforming in some models. The study even introduced a MAF, modified absolute function, that scaled negative inputs, proving that tailoring activation functions to data characteristics can unlock better performance. So what does this mean? It's a reminder that AI isn't one-size-fits-all. For fNIRS, where signals are noisy and complex, choosing the right activation function can make the difference between a good model and a great one. It's like picking the perfect tool for a job. Sometimes the old standby isn't the best choice. This research isn't just about fNIRS. It's a blueprint for adapting AI to specialized data. Next time you hear about brain-computer interfaces or neural decoding, remember, the secret sauce might be hiding in the math of activation functions. Thanks for watching. If you want to dive deeper into how AI deciphers the brain, hit subscribe. And let me know in the comments, what other AI mysteries should we unravel? Ever wonder how your brain processes sounds, or how computers learn to do it too? Today, we're diving into a fascinating study that explores how different activation functions in neural networks, those little math rules that help AI learn, can make or break performance, especially when analyzing brain data from a special technique called fNIRS. So what's an activation function? Think of it like a neuron switch. When your brain processes information, neurons fire based on inputs. In AI, activation functions decide whether a neuron wakes up to pass along data. But not all switches are the same. The researchers tested 4 versions, tweaking a parameter called alpha to see how it affects performance. They tried alpha equals -2, -1, 0, and 2. Here's what they mean. Alpha equals -1 acts like the absolute function, treating positive and negative inputs equally. Alpha equals 0 is similar to ReLU, a popular choice that ignores negative values. Alpha equals -2 scales the negative side more, while alpha equals 2 does the same but keeps the sign. The goal? See which activation function helps neural networks best interpret brain signals during an auditory task. The team tested these functions in 4 different neural network designs, each with its own way of processing data. For example, fNIRS net and absolute net use dual-branch systems to capture both spatial and temporal patterns, while MDNN and shallow convnet take simpler, more direct paths. But what's the data they're analyzing? It comes from a study where participants listened to sounds, while researchers measured brain activity using fNIRS, a non-invasive method that tracks blood flow in the brain. Think of it like a brain scanner that uses light to see how oxygen levels change when you hear a tone. The dataset includes 1,836 trials, each labeled as either a deviant tone, the one you're supposed to notice, or a standard one. Now here's where it gets interesting. The researchers ran 5-fold cross-validation, like a rigorous test where the model learns, checks its work, and then proves itself on new data. They measured accuracy, sensitivity, and specificity, basically how well the model detects deviant tones and avoids false alarms. The results? some activation functions shone brighter than others. For instance, Tanh and absolute functions consistently outperformed others across networks. Tanh, which smoothly handles both positive and negative inputs, hit 83.66% accuracy in one network. The absolute function with its symmetrical mirror behavior was also a standout, especially in deeper networks. But not all functions were equal. ReLU and square lagged behind, while ReLU, the alpha equals 0 version, struggled in some models. The real twist. A modified absolute function with alpha equals -1 beat others in tests, suggesting that symmetry, when matched to data characteristics, can unlock better performance. Why does this matter? Well, fNIRS data is tricky, noisy, sparse, and full of subtle changes. By choosing an activation function that matches the data's characteristics, the model can learn more effectively. The researchers even did a special analysis, MAF, to confirm that symmetrical functions like absolute beat others in accuracy and consistency. This study isn't just about fNIRS. It's a blueprint for adapting AI to specialized data. Next time you hear about brain-computer interfaces or neural decoding, remember, the secret sauce might be hiding in the math of activation functions. Thanks for watching. If you want to dive deeper into how AI deciphers the brain, hit subscribe. And let me know in the comments, what other AI mysteries should we unravel?